So in this particular problem, we have a disk of radius 0.8. It rotates from rest and it speeds up to an angular speed of 32 rads per second in a time of 0.8 seconds. And this is assumed to, or it says to assume uniform angular acceleration. All right. So here's A, B, C, D, and E. If you need to, pause it and keep up. So here's a little visual for you. Here's a disk of 0.8 meters, and it is currently rotating in the counterclockwise direction. Okay. So part A wants us to find the magnitude of the angular acceleration in the disk. So based on the information we are given, I would just go ahead and apply the average acceleration function here. Average angular acceleration is just a change in angular speed divided by change in time. So I'm just going to go ahead and break this up into omega f minus omega I. So hopefully by now your linear kinematics is good. This function here just mirrors average acceleration linearly. So omega I is 0 because it says it starts from rest. So here omega f is given as 32 rads per second. Time is given as 0.8 seconds. So really it's just plug and chug. Okay. So 32 rads per second divided by 0.8 seconds. And that'll give you an answer of 40 rads per second square. And it says magnitude, so I don't really need to specify whether it's rotating like clockwise or counterclockwise or positive or negative direction. So that's just the magnitude. Part B asks us to find through what angle does the disk turn. So in order to find the angle through which it turns, you can just use the angular displacement function. Why? Because we have a lot of information already. This is just one way to do it. Here, omega I is 0, so I'm just going to cross that term out. I just found angular acceleration, which is 40 rads per second squared. The time here is 0.8 because it's given in the statement here. All right, other than that, it's just plug and chug. So this function reduced down to just pretty much just 1/2 alpha t squared. Once again, alpha is calculated in part A, t is given. Calculated work time, that should give you about 12.8 rads. Okay, so the unit here for angular, or the angle here is in rad. Unless otherwise specified, you should just keep it in rads. All right, let's go ahead and do part C. Calculate the number of revolutions completed while coming up to speed. So it wants us to find how many revs it has completed as it rotates from rest to 32 rads per second. So this is just to help you in case you don't understand rads and revs, the relationship between them. Here on my diagram, I just go ahead and put the x and y axis there. So according to the unit circle, here is 0 rad, and then at 90 degrees is pi over 2 rad, and then at 180 is pi rad, and then at 3 halves pi, or 3 pi over 2, that's at 270 degrees. And then if you go all the way back to where you started, which is 2 pi rad. So this information helps you make this correlation that for every 1 revolution, which is just 1 cycle, it is 2 pi rad. So really, I'm just going to take the answer I've calculated in part B, which is 12.8 rad. Okay, and then I'm just going to multiply it by this conversion factor. Is for every 1 revolution, 1 cycle, 1 lab, it is equivalent to 2 pi rad. The unit for rad will cancel out. So as you can see, it would just be 12.8 times 1 divided by 2 pi. So if you punch in your calculator, you should get about 2.037 revolutions. So it's spun around at least twice. Okay, a little over 2. All right, let's go ahead and do, what is it, D. D asks you to find the tangential speed of a point mass of the disk at 0.8. So here's a little point mass on the very, very outer edge. So to do so, this is V tan. So in my diagram here, this arrow that just came up, this is your tangential speed or tangential velocity, if you want to include direction or not. So here, the tangential velocity function is just given by r omega, r being the radius, or in this case, where the point mass is relative to the center. The center of this disk is right there, is being spun pivot at the center there. So that is your distance, and that happens to be r as well. Omega, we already know. So really just plug and chug here. R is 0.8 meters. Omega is given as 32 rads per second at 0.8 seconds. And if we simplify this on our calculator, you should get about 25.6 meters per second. And so that is your tangential speed. Keep in mind, tangential velocity is different because the direction keeps on changing. Okay. Let's go ahead and do E. What is the magnitude of the tangential acceleration? So of this point mass again. So here it asks us to find A tan, but we know A tan through this relationship. A tan is simply the radius or the distance from point mass to center or pivot here times the angular acceleration. Here we are given both of these already. R is 0.8. We found angular acceleration for this one as 40 rats per second squared in part A. So plug and chug, 0.8 times 40 is just 32. And the unit here is meters per second squared because it is tangential acceleration. Okay. All right, and this is magnitude, so we'll just keep it as that. And then part F wants to find the magnitude of the radial acceleration of this point mass again. Well, radial acceleration is the same as centripetal acceleration, and your prior knowledge should hopefully lead you to here. Centripetal acceleration, or radial acceleration as it is known also, is v squared over r. But here I substitute out v. V, according to my cursor here, the relationship between linear and rotational motion kind of goes to this function here. V is equal to r omega. So instead of v, I just substituted out v for r omega. I put it in the parentheses, and then the square terms remain. Here, I'm just going to distribute the square term to r and omega, so I get r squared omega squared over r on the bottom. So as you can see here on the top, you have r squared. On the bottom, you have an r, so one of the r's will cancel out. So I'm just going to cross out the exponent 2. I'll keep the r here because there are 2 of them on top multiplied together. And other than that, it reduces down to just r omega squared. So this is the new, quote-unquote, new function for radial acceleration or centripetal acceleration if in terms of omega. Okay, r is given, omega we already know, r 0.8, omega at 0.8 second once again is 32 rats per second initially given. We're going to square that, and that will give you a value of about 819.2 meters per second squared. And this is magnitude, so I am done. Okay, all right, I hope that helps. Stay nerdy, don't be wired.